Thank you, Lance. Thank you, Lance and Alexei and Igor for organizing this workshop. That's been really eclectic and interesting. So my talk is going to be, it's relatively early morning, so this is going to be a very simple talk. No non-invertible symmetries, no cats, So this is mostly work that Yigal Shamir at Tel Aviv University and I have been doing. So here's a list of papers. The ones in red are the ones that I will touch upon in this talk. I wanted to highlight Thyro Brown, Sven, and Andrew Freeman, who are all master students, but they got involved in some of the parts of this project. Okay, so here is sort of the reason we got interested in this. So these are, this is the spectrum of SU3 gauge theory. So it's QCD-like, but with NF equals 8 light fundamental flavors. So we just increased the number of flavors. And this is the same theory that Anna has been talking about. I know. We'll wait for the end of my talk. I have some questions. I have some questions for you. Yes. Okay. Yes. I'm sure that there will be some. Okay. So so this is the spectrum where you have various hadron masses normalized by f pi as a function of the fermion mass in the Lagrangian, again normalized by f pi. And so what you see if you compare this with the same type of plot, if you would also look at it for QCD, is you see there is the green points here are a light scalar that at least for these fermion masses are about degenerate with the pion. So there's a stable a scalar in this theory. And you also see something else, that basically these ratios don't depend on the quark mass. So this looks like an approximate hyperscaling. In QCD, that same ratio m pi over f pi would go like the square root of the quark mass, and you don't see that behavior here at all. And I don't show that here, but these simulations were done with staggered fermions, and so I will later have something to say about T-splittings as well. Similar results have been seen in SU3 gauge theory of NF equals 2 sextet fermions, but I'm going to concentrate on the NF equals 8 theory. Okay. And so the hyperscaling suggests that this may have something to do with the scaled symmetry. And well, it works. So what I'm going to do, so first of all, we all know already that SUN gauge theory with NF fundamental flavors has, at low NF, it's confining and chirally broken. At larger NF, you enter the conformal window. Very close to the conformal window, the theory may be walking. And so what is not known, I claim, is what NF star is. So Anna would now claim that it's equal to 8, with a very good position. But I think there's still open questions about that. So anyway, I'm going to take the approach. I'm going to assume for the rest of this talk that NF equals 8 is below NF star, so that it's close to the conformal window, but it's not inside or not on the sill or not inside the conformal window. And so then we have chiral symmetry breaking, and so there are going to be pions, and so we need to construct an effective field theory to see whether we can understand these simulations. But of course, if we have an effective field theory with a spectrum like this, we need to include all of these states, at that same mass in our effective field theory. So. So this plot is from, I think, from the 2018 paper.
Yes, there is a 2022 paper with exactly this, with extended data and much better error analysis, right, where the sigma actually peeled off from the pion. It doesn't look that light anymore, but that's beside the point. The other one is that it looks like hyperscaling. You mentioned the sextet model, which also shows hyperscaling. I want to say that 12 flavor, which has a very clear infrared fixed point, looks exactly like that. So somehow that is a very universal behavior. Yep. And the data that went into it is really not showing any level of chiral symmetry breaking.
wait until the end of the talk.
Okay.
For now, I'm going to just assume, and I don't, to be very clear, I don't know the answer, okay, but I have some questions based on what we did that I...
So whatever you do is independent of that up to the point where you start fitting the data. Certainly the analytical calculations are solid, and you can use it for whatever you want. I am just objecting to using it for any favors.
The situation is going to be that I think the data are not good enough to decide the issue. But anyway, no. Please ask all the questions again at the end of the talk. Okay, so what I'm going to do is I'm going to construct the effective field theory. We'll call this Dilaton chiral perturbation theory. So it's basically chiral perturbation theory with an extra dilaton in there. And so I'll talk a little bit about the power counting. You need a systematic expansion. And then, once we have set that up, I'll just look at it at tree level. One of the reasons we have looked at beyond tree level, but there's not good enough data to be able to go beyond tree level. And I'll talk about something called the large mass regime and hyperscaling. So my point is going to be that Dilaton chiral perturbation theory tells you that if the fermion mass is relatively large, even if you're in the spontaneously broken phase, it can look like hyperscaling. Okay. And so then I will talk about, there are two papers that have these type of data, like I showed. There's the LSD collaboration, and there's an older paper by Japanese collaboration that is no longer in existence, and I'll talk a little bit about that, and then I have some open questions, in particular for Anna, and so they hopefully lead to future work. All right, so of course, the theory, so I'm going to assume that I'm below the conformal sill, so there's chiral symmetry breaking, but I'm close to the conformal sill, and so therefore, I'm very near an infrared fixed point. The theory contains, of course, pions. That's the usual story. They become massless in the chiral limit. So what I'm going to assume is that scale invariance gets restored in the infrared when NF goes to the conformal sill, and that I'm going to be close to that. Of course, basically by changing NF, we're moving around in theory space. NF takes discrete values, certainly if you do it on a computer. And so a technical point is that you can make it a continuous parameter in the Veneziano limit, where you take both NF and the number of colors to infinity, keeping the ratio fixed, and it becomes a continuous parameter that I can play with. This is just a technicality. But what the main assumption is going to be that I'm close to a point where scale symmetry gets restored, so that I can think of this 0++ state that we do see in the simulations. Now, maybe it has nothing to do with this, but we do see it in the simulations, that it's a pseudo-number Goldstone boson associated with the breaking of approximate scale symmetry, which would become massless if I move to the conformal sill and, of course, also take the chiral limit. And in order to make this all work, there are some technical assumptions on the dilaton potential that you need to assume, but I don't want to make this a talk about any technical details. All right, so this is again the usual statement about chiral symmetry that we all know. Then if there's a dilatation current, which is proportional to the energy momentum tensor, and the main result is that if you look at the divergence of this, that gives you the trace of the energy momentum tensor by just hitting S mu by d mu, and that has two parts. There's the classical, so this is not equal to 0. There's the classical part that, of course, comes from turning on a fermion mass that breaks scale symmetry. But then, back in 1977. People calculated what's called the trace anomaly, which has two parts, a gluonic part, and then if you turn on the fermion mass, there's a fermionic part as well. Okay, and so if I'm in a walking regime, the beta function becomes very small because the coupling is running very slowly. So this, in some sense, becomes a small quantity as well, just like this would become small in the chiral limit. And so we're going to assume that the anomalous part of the trace of the energy momentum tensor is of order the distance to the conformal sill. Remember, NF is just, it's basically the number of flavors normalized by the number of colors. So this is the value at the conformal sill, and I'm going to assume that NF equals 8. If NC equals 3 is a little bit below that. And of course, if I do the Veneziano limit, there's order 1 over NC corrections, and there's chiral corrections. And so what we would like to have is an effective field theory with a systematic expansion in these parameters, right? The quark mass, fermion mass, the distance to the conformal cell, p squared, and 1 over nc. Okay, and so we would assume that just like the pion mass squared goes like the the thing that breaks chiral symmetry, the dilaton mass squared would go like the distance to the conformal cell and then have chiral corrections.
Where is this why with respect to any dilaton? Why is there dilaton is usually associated with some spontaneous breaking of conformal symmetry?
Well, so but we're below the conformal cell, so there is you turn on some this turns on basically some scale symmetry breaking, right? So this is why I think of.
It's explicit. You just have beta function. Conformal symmetry is explicitly broken.
Yes, but
why would there be any ghost component?
The beta function turns on, when I go through the conformal cell, right? I mean, at the critical point, at the infrared fixed point, this is equal to 0. You go a little bit below the conformal cell, beta turns on, just like you can turn on a quark mass, and it breaks scale symmetry, and in the infrared.
There is some fixed points nearby in the field space, and a G-flow plus is near this fixed point. That has nothing to do with spontaneous breaking of conformal symmetry.
There's a continuous parameter.
Okay. So it's in the number of flavors.
Sorry?
The breaking is in the parameter of the number of flavors in some sense.
Right, but it's the number of flavors that tells you how close you are to the conformal cell.
Walking beta function, there is a fixed point in the complex plane of the coupling constant.
Right.
There is a beta function is small when you pass by near this fixed point.
Right. So the assumption is that this is a tunable smallness, right, by the number of flavors.
That's an overall IR scale. So there will be lambda QCD, it will be exponentially small in the square root of an f minus nf star because our G flow is slow, so it takes a long time.
So there is a parameter that tells you how small or large this breaking is.
So all of the masses. Okay.
Revisit this discussion in the discussion session.
Right. Okay. So how do we build? So this is the underlying Lagrangian of the theory. So what I'm going to do is I'm going to build my effective field theory in the usual way by introducing spurions. This is the well-known spurion field for the quark mass, and then so I'm going to think of this as regulated in in d dimensions, and then of course in d dimensions you need another spurion in order to make this thing scale invariant. So this theory here is scale invariant if you have the spurions transform like this, where lambda is the scale parameter, and so this spurion sigma transforms like this here. Okay, so with that, this whole thing transforms into lambda 4 times itself, and this is what a scale invariance is. And of course, if you set the spurion fields equal to their expectation values, which for chi is the quark mass and which for sigma is equal to 0, then you break the scale invariance and you get the theory. And so if we want to build an effective field theory, you introduce the usual nonlinear pion field that transforms exactly like its corresponding spurion, and we introduce an effective field for the dilaton, which transforms like its spurion partner. Okay, and so those are the building blocks for building an effective field theory. So here is the lowest order Lagrangian for the effective field theory. So you recognize, this part here is the kinetic term for the pions. This part here is the mass term for the pions. Of course, there's also going to be a kinetic term for the dilaton. There's going to be some potential. E to the 4 tau is invariant or transforms to a lambda 4 times itself under a scale transformation. And then, of course, because of the simple transformation laws of sigma and tau, the difference between them is basically invariant. So you can multiply each of these terms with an arbitrary potential of the difference. Okay. So before I get to discuss these potentials, let me make another comment. So we are expanding around the fixed point. Now in this theory, chi, or the mass, which is the value of the spurion, is equal to the renormalized mass, so it transforms with an anomalous dimension, and we take that anomalous dimension to be the anomalous dimension at the fixed point because we're expanding around it. corrections to that are supposed to be built up in higher orders in this effective field theory, okay? Now, of course, so these potentials are arbitrary functions of their argument. Nothing in what we've done so far tells us what these potentials are. So without any more information, we have no predictability in this theory because if you think about Taylor expanding these potentials, you have an infinite number of low energy constants, okay? And for those of you who are familiar with, trying to get the eta prime in chiral perturbation theory, in a large NC expansion, the same type of issue happens, when you try to incorporate in 1 over NC, you try to incorporate the eta prime in chiral perturbation theory. Okay, so here is a cartoon slide about why we think we can get control over those potentials. There's a lot more work that goes into this, so this is just a cartoon version of the argument. So if I look at the renormalized microscopic theory, that's and expanded in powers of this scale spurion sigma, then of course you get the theory, the microscopic theory, when you set sigma equal to 0, and then there's just an expansion in power of sigma, and of course the first term there has to give you the trace anomaly. And so if you take of course, we should do this at the level of path integrals and so on, but again, this is the cartoon version. So if I take the derivative of the microscopic Lagrangian, the renormalized microscopic Lagrangian with respect to the spurion, then set the spurions equal to 0, of course I pick up precisely the gluonic part of the trace of the energy momentum tensor, and by assumption, this is small, proportional to the distance to the conformal window, right? So that's one of our small parameters. And if I take more derivatives, I get more powers of this small parameter, okay? On the EFT side, if I start taking derivatives, right, I have to take derivatives with respect to this sigma here, okay? So I take derivatives of these potentials, and if I think of these potentials as Taylor expansions in their argument, okay, then we see that the coefficient Cn, after taking n derivative, has to, in order to match the underlying theory, has to be of this order. So the result of this is that what you find is that these coefficients, are organized as a power series in, each of these coefficients is a power series in this small parameter that starts at order n. And so this is the way that we start getting control over these potentials. Of course, there's a lot more work needed. First of all, I have 4 of these potentials here, so I need to look at cross terms, I need to look at loops. So there's a lot of work that goes into convincing yourself that this power counting really works. So all the details are in that paper, but that's all lots of technicalities in power counting, so I don't want to really go into that. Okay. So at that point, so we can basically, in the leading order, okay, so if I work the leading order in chiral perturbation theory, I just have to keep the leading order constants, the C0 here, except for the Dilaton potential. And so I can basically set all these potentials equal to a constant, which I can absorb in these low energy constants here. So in other words, I set them equal to 1. This term here starts off, these terms start, this is order p squared, this is order p squared, this is order the quark mass. This term starts at order 0 in my small parameters. So there I have to keep 2 orders, which is what I'm doing here. There's a term that's constant and there's a term that's linear in tau. What I've done here, of course, there are 2 independent constants there, but what I've done here, I've allowed myself to do a shift in the tau field to basically force the expectation value of the tau field to be equal to 0 when the quark mass is equal to 0, right? And so choosing these coefficients in that ratio after that tau shift precisely does that job, okay? So now what I claim is that this is the leading order effective field theory for a systematic expansion in powers of p squared, the quark mass, and C1 here is a coefficient of order, the distance to the conformal silk. Okay. All right, so we can look at leading order predictions. First thing we have to do is we have to minimize the potential, find out where, so what I'm saying here is that these coefficients, the shift has been chosen such that the tau expectation value is equal to 0 when the quark mass is equal to 0. When you turn on the quark mass, it's going to be dependent on that. If the quark mass is positive, this part of the potential is minimized by setting sigma equal to 1, okay, so the standard thing. And so then I need to minimize the potential as a function of the dilaton. And so that leads to this saddle point equation, where this capital M is basically setting the scale of the theory. It's all these combination of all these low energy constants. And then you can look at, you can expand to quadratic order. You find the pion mass squared, you find the dilaton mass squared. What you notice is that because of the scale symmetry, there are these exponential factors here that I need in order to make this theory scale invariant. And so, if tau gets an expectation value that depends on the quark mass, these factors e to the v, where v is, by this equation, a function of the quark mass, show up also in the renormalization of the decay constants, and for that matter, any other hadronic mass in my theory. Okay? So in my power counting, m, the fermion mass, and c1, which is the distance to the conformal sill, are formally of the same order. But of course, I can study different regimes. I can take the regime where m is smaller than c1, and I can see what happens if I take m a little larger than c1. Okay? If I look at what we call the small mass regime, so where I take this combination much smaller than 1, okay, then what you see from this equation, if this is very small, then v has to become very small. E to the v becomes approximately equal to 1. The pion mass squared, you just get the usual, GMO relation, and the dilaton mass squared, the quark mass corrections become very small relative to the distance to the conformal sill. So those are then the predictions, and in particular, the pion mass gets much smaller than the dilaton mass, so you just decouple the dilaton and you go to standard chiral perturbation theory. Okay? But you can also look at the large mass regime. Okay, so now if I look at this saddle point equation, now if the left-hand side becomes very large, the exponential here dominates, so I can ignore the little v here, and so then basically I get a prediction for e to the v, which is this thing, right? Basically taking the 1/1 plus gamma star power of this. And what you see is that since this factor e to the v shows up in all of these masses here, right? There's the mass squared has the e to the 2v, this mass squared has the e to the 2v. Now, basically, what that predicts is that there's sort of it looks almost like a universal behavior where all of the mass scales in the theory start showing, this behavior as a function of the quark mass, which is what is hyperscaling, right? Of course, this is just only in the large mass regime, okay? Whereas if you're inside the conformal window, the only source of scale symmetry breaking is the fermion mass, so then this hyperscaling is exact. But if the mass is large enough, if the mass dominates the slow running of the theory, so the breaking of scale invariance because the theory is walking, then the mass deformed theory, then this theory is going to look like a mass deformed conformal theory. Okay. Thinking a little bit about the expansion parameters. So the one thing that I should stress, that even though all of these masses scale in the same way as a function of the fermion mass, m pi squared and m tau squared are still parametrically lighter than other hadron masses, because there's still this coefficient C1, which is the distance to the conformal sill that governs their smallness. Okay, and in particular, if I look at the loop expansion parameter, m pi squared over 4 pi f pi squared, using these results here, if I take this and I divide it by that thing squared, the e to the 2v drops out. And I basically get that this ratio goes like this. So this is not small because the fermion mass is small. It's small because the distance to the conformal sill is small. If you stick in this solution, right, then it depends on the fermion mass, but it depends only logarithmically on the fermion mass. So as long as this, you can make this fermion mass very large, as long as this combination is small, as long as this log doesn't become ridiculous, you are still within the region of the validity of the expansion. Okay, this is of course very much unlike QCD, because in QCD C1 is just a number of order 1, and therefore this would not work. Okay, so what I claim is that Dilaton chiral perturbation theory has a large mass regime that is still accessible to this effective field theory, and that and that will have some consequences. And what that tells you is that this theory can behave like a hyperscaling theory, even though I'm below the conformal sill. Okay, so what I would like to do is fit data. Now, one of the problems is that these simulations are very hard for very many reasons that Anna knows better than I do. So there's not a lot of data available, but I'll try. Okay, so I'm going to use, of course, I'm going to use the exact three-level expressions. Okay, so I'm not going to assume that there's this hyperscaling. I'm just going to use what Dilaton perturbation theory tells you to do. I should warn you that these simulations have been done at only one lattice spacing, so we have basically little to no information about lattice spacing dependence. So I'm assuming here that the lattice spacing is small enough that it makes sense to fit this data, but this is something that I cannot answer. Okay, and the quantities that I will fit are m pi squared over f pi squared, a times f pi, a is the lattice spacing, and this ratio. And so here I again wrote their three-level relations in terms of some combinations of low energy parameters. It's not important what they are. Okay, so what we try to do is fit these data. So here are the data for these quantities from the LSD collaboration. So what Anna pointed out is that these data have become a little bit more precise. I still don't think these data are clearly not going to have a lot of influence on the fit because of these large error bars. I think the error bars are still so large that, if we would redo this with their 2022 data, it would not make a lot of difference. Okay, and so what you see is that, if you look at these plots and you look at p-values, you get good fits. You can do this. These fits, these three plots. So they have 5 different fermion masses. So we have basically 10 data points here. Officially, we have 15 data points, but as I said, these data points don't do a lot to the fit. And so we have done several fits. We have fits where you do the fit over the full range of 5 masses. You can also do a fit where you drop the highest mass. You get good p-values in both cases. Now, as you can see, these are fits where we did not include the highest point, so this point is a little bit off, but either way, it basically works. So Dilaton perturbation theory on these data works. Okay? Of course, what we also see is that there's a lot of curvature in these plots when you go to what I would call the small mass regime, and the curvature really falls outside the region where the data points are, right? So this is always somewhat of a dangerous situation because you would like to have data points in the region of the curvature to really check whether this works. So I'll come back to that point. Okay. There's also data from the LAT-KMI collaboration who did their simulations before LSD. Okay, thank you. And so it's basically the same theory that they simulated, however, with a different choice of lattice action, a different Baire coupling, and so it's hard to compare because also only at the one lattice spacing, so it's very hard to match the two theories on each other because they're not the same action. But their mass range, so this is the Baire mass range, right? The Baire mass range of the LSD collaboration was this. Okay, so this mass range here is at much larger masses than the LSD simulation. And even though you cannot directly compare those because these are different actions, I think we have reasons to believe that also the renormalized LAT-KMI masses are distinctly larger than the renormalized LSD masses. So they have actually 10 masses, so they had many more masses. Of course, it was easier for them to do because at larger masses, these simulations are easier. And so if you try to fit, so they have some Dilaton mass data, but they're even worse than the LSD Dilaton masses. This is a hard calculation. It's not because these collaborations don't try to work hard, but there's disconnected diagrams and so on. So these scalar masses are hard to measure. So if you try to fit the data for m pi and f pi, for which you have 200 data points, over the full range, the p-value is 10 to the minus 11. So this does not work. Okay. We have looked at NLO. So at NLO, there are many more parameters. So even though you have quite a few data points, it becomes very hard. There are many parameters that we cannot really determine from the fits. Okay, we can get a good description. What looks like, if you plot at the curves on top of the data points, you can get a good description at NLO if you just arbitrarily choose some of these parameters to be 0, so that you can do a fit. However, if you then inspect what the size of the NLO corrections is, they're very large compared to the corrections for the LO contributions. And we think that the reason for the breakdown, so basically what we're saying that Dilaton perturbation theory breaks down for the Lat-KMI collaboration, and that might be that because they're at a larger mass range, okay, so you know, and in fact their largest pion masses are almost equal to their rho mass, so that starts to be outside the region of this effective field theory. And so what we think is that these larger masses take this theory too far away from this infrared fixed point, even if our assumption would be correct that in principle NF equals 8 is just below the sill, okay? We can, so that would mean that, you know, the coupling starts running, so the mass anomalous dimension can start moving. So we have a model where we can model that behavior and then we can do good fits, but we're then outside the region of strict Dilaton-Chiral perturbation theory. Okay. One thing that I wanted to mention, I'll be very quick because I'm already almost out of time, is that all of these simulations for both Lat-KMI and LSD were done with staggered fermions. In staggered fermions, there's something called taste splitting. The staggered fermions don't have the exact flavor symmetry of the continuum theory. And the pattern of taste splitting, so if you look at the pion multiplet, then it's very, very different the way it looks like from QCD. This is an old plot from the Milk collaboration where they show the taste splittings as a function of the fermion mass. You basically see that that all these lines are parallel, whereas here the size of the taste splittings clearly depends strongly on the fermion mass. Okay, and we can model this also in our effective field theory, so I'm not going to go into how that all works, but again, there's these powers of e to the Vm showing up in all of these taste splittings as well. So we can describe these taste splittings pretty well if we do assume that we model the anomalous mass dimension. You can also do this for the LSD taste splittings, but they didn't measure as many. They only measured 2, Lat-KMI measured many more of these taste splittings. So here, staggered fermions, a bulk of staggered fermions is kind of turned into a feature. This suggests that Dilaton-Chiral perturbation theory does a good job understanding something. Okay, so I'm getting to open questions, so I'm almost at the end of the talk. So let me go back to this plot, for instance, f pi. Okay, what you see is that, so this does not go to 0, but the value at m equals 0 on this plot you cannot see. Okay, because there's this huge, we're in the large mass regime, and so there's this huge nosedive that f pi takes when you go to the chiral limit. And so if we look at the LSD fit, then you find a little f pi is the value of f pi in the chiral limit. So it's very, very, very small, okay, and of course with a large error because this is very long extrapolation, okay. Whereas the values in the LSD simulation, so the values of f pi at the fermion masses at which they measured, are of order this size, okay? So we checked that, their volume is large enough that f pi at the masses which they simulate is large enough that an effective field theory should apply, okay? But if you want to go to smaller quark masses, because of this very strong dependence on the quark mass, also of f pi at 3 level, in order to have f pi fit in the box in the chiral limit, you would require incredibly large lattices, which is out of the question. Okay. In other words, what I'm claiming is that if my assumption is right, that this effective theory describes these data, is that both the LSD and Lat-KMI simulations are very deep in this large mass regime. It's a very long extrapolation to the chiral limit, and so we see approximate hyperscaling. And at least for these simulations at large masses, this suggests why it may be so hard to distinguish, whether you're below or above the conformal sill. Because, below the conformal sill you see hyperscaling, above the sill you see hyperscaling, so how do you distinguish? Okay. Now, of course, I have my questions for Anna, because Anna has recently been doing these simulations that she was telling us about 2 days ago, with at 0 quark mass. Okay, and so that means that there are 2 possibilities. First of all, we should study, so she showed a spectrum that looks like hyperscaling, basically for the finite size scaling that would be totally consistent with it being inside the conformal window. So there are 2 questions that I have. It could be that I would like to see what, in this case, the effective field theory should be studied in the epsilon regime. But if this is true here, if indeed we're in this very large mass regime and f pi in the chiral limit is much, much smaller than what you see in this simulation, then I would say that AMA is in the femto universe. So, and that's where I would also expect 1 over L for masses. So I think there's a big open question as to what these results actually mean. So I'm not claiming that you're not right. I'm just saying there's a big open question that will be not easy to resolve. Okay? And of course, it's based on a very long extrapolation. One more thing that I wanted to do, because I sometimes get that question, is QCD maybe in this class? It's NF equals 2 or 3, but maybe that's close to the conformal window. So I cannot answer that in general, but I can apply Dilaton chiral perturbation theory to it. So we know, so then the sigma particle will be the part of this 0 plus plus state, which of course in QCD is unstable, but that's maybe just because of the quark mass. So the parameters of the sigma are very well known. So you can calculate in 3-level Dilaton chiral perturbation theory what the tau decay, what the Dilaton decay rate into 2 pions was. Here's the formula, and you use the parameters. You assume that this ratio is not larger than a half, okay, which is a very mild assumption. This goes like square root of NC, this goes like NC, and so you find a prediction that is basically about a factor of 10 smaller than the actual width of the sigma. So I think, Dilaton chiral perturbation theory, if it's right, tells you that QCD is very far away from the conformal still. That's all I wanted to say.
Alexei?
So I'm an outsider to this, and I was confused. Like, why do you think that there should be a dilaton at all? It's the same question as Victor. Why do you think there's a dilaton?
Well, I don't know whether there's a dilaton, but what I do see is this light scalar state. And so Anna's right, it starts peeling. If you look at their 2023 paper, starts peeling off from the pion a little bit, but it's still much, much lighter than in QCD, at least at the quark masses where it was simulated. Not really. I also, okay, but so what we want to do is we want to see, so if I want an effective field theory description of this, I need to include that state, simply because it's more or less degenerate, with the pion, right? I can, and so either it's an accidentally light state for no good reasons, and then I don't have a principle to build an effective field theory, or I have to make some assumptions about it. And then, this is what we're doing. So I'm not saying that I know that this is a dilaton. I'm saying let's assume it's, a cousin of a dilaton, and then we have an effective field theory description, and let's see what we learn from that.
Is the scalar still heavier than the pion?
So well, so the arrow bar, the green, so the black points are the pion, and that can be measured. That's connected diagrams only, so this can be measured very well. So the arrow bars are within the size of the points here, but the green points are the scalar mass. This is 0 plus plus, and so they have larger errors because this is numerically hard, right? But if you look at this plot, it's basically degenerate with the pion.
Okay, Aida had a question here, then we'll come back to this side later.
Yeah, so this is actually taking the discussion in a different direction. I'm interested when you do the fits to the LSD and LAT-KMI data, whether, I don't know if those papers reported correlations and if the correlations are included.
Good question. So for the LSD fits that we did, correlations are fully included. So we joined forces with Ethan for that. Okay, so the correlations we know, so we did the proper fits. For the LAT-KMI, we could not do proper fits because that collaboration is defunct, and we tried to trace it, but there was no way that we're going to get correlation matrices from them. So we had to just go by the tables in their papers, and that's all we could do.
Did you assume 100%
I don't remember whether we played with that, so I would have to look that up. But but I think the message doesn't change. I would be very surprised if correlations would change anything in the message. Is that there's sort of starting to be in a mass regime where this effective field theory starts breaking down.
I mean, it's just the goals whether you can actually get accurate shape information.
Yes.
Data are highly correlated.
Yes. Right. Yes, right. But there's no way that and the collaboration doesn't exist anymore, and it now goes back to 2017, which is an eternity when it comes to preserving data. So.
I am cursed because I know the lattice data. And a couple of comments. So you are absolutely right, and that's why I put in my talk a disclaimer that a numerical simulation, of course, cannot prove whether NF8 is below or above or right at the conformal window, because I cannot exclude the possibility that if I go to, well, we had 36 cube as the largest volume, maybe if I go to 3000 cube, something will happen. It's not going to happen in practice, but in principle. But I can state, and I stand by it, that this system has a strongly coupled phase that is separated by the weakly coupled phase by a continuous phase transition. Mm-hmm. So if it happened, if it turned out that the system is actually chirally broken in the weak coupling phase, then you are proposing a scenario where we break chiral symmetry, then we undergo a second order, a continuous phase transition, and restore that chiral symmetry. That is quite an unlikely scenario. So that's one thing.
You know my complaint about that. I think going into that strongly coupled phase, you may restore chiral symmetry, but you break Lorentz invariance. I think it's really
we can discuss. I disagree with that, but that's.
So I don't know what that phase is.
It's a continuous phase transition of a statistical system. Mm-hmm. I am not claiming anything about QCD. The other one that refers to fitting the LSD data. Sorry. Your picture is that there is a nearby infrared fixed point that you assume is a little bit above NF8, and the data captures the properties of that infrared fixed point. Mm-hmm. Now, this is an extremely slowly running system. I think we all agree on that. We have measured the beta function. So you would really have to have a very large energy scale or change of energy scale to move from a given coupling to another coupling. Mm-hmm. We have done simulations. Yes, it is unpublished because my student is busy with other things, but I can show you, if you want to see it, that the renormalized coupling in a given scheme is about 10, where the LSD data was taken, and we can push that renormalized coupling to about 30.
This is with the Pauli-Villais trick, I guess.
Yeah. And but we match the 10, we reproduce everything up to 10, but we can go to 30. Right. And there is no fixed point yet, maybe just 20, it doesn't matter. Go from G squared 10 to G squared 20 probably needs a couple of orders of magnitude in scale change.
Yes.
So there is no way that a lattice calculation done at G squared 10 can say anything about what happens at 20, and even 20 is not at the fixed point.
So I don't know
it's not your fault, but that's the fact about the data.
Mm-hmm. Well, so I think it could be that the LSD simulation, where they simulate it, is so far away that we cannot say anything.
That's all I am saying.
Right.
And when they started the simulation, that was the best they could do.
Right.
But we are 10 years beyond that.
Right. But I mean, the one thing that I find interesting is that, so Dilaton perturbation theory does give a good fit. Now, with all the caveats that I mentioned, what I find more remarkable is that we can fit the taste splittings very well. Right? The taste splittings in this theory behave very different from in QCD, and we can fit it. Right? So this is, this is something that I would need an explanation for, because if you're very far away, if your coupling is still running, it should be more QCD-like. Taste splitting should look like in QCD. They don't look at all like in QCD. And so, we have you have a field theory that understands that. So, you know, so I think there's a bunch of open questions. Right.
I just want to make another comment on this Dilaton business, right?
Sorry, can I say one more thing to Anna? So you say they look conformal, and I know you want to be in a conformal phase, but if your coupling is still so far away from the infrared fixed point, you know, for the LSD data, then that is not a very strong statement, right? Right.
Okay, so if this data is correct and there is some reason to have a light dilaton in this business, that would be very interesting. But I just want to say at the moment there is no theoretical explanation for this, because if a RG flow passes close to a fixed point, for example, we can start with a three-critical Ising model and tune the parameters so we pass very close to just usual Ising model and then gap out. RG flow will be long because you're spending lots of time near a fixed point, but there is no reason to expect a light scalar field in this setup. So your setup is identical to this. Now, there are holographic models where you basically have ADS space and you put some IR brain, and that indeed spontaneously breaks a conformal symmetry. And in those holographic models, there is a light dilaton, and then you can make slightly massive and whatever. But to have this, you need a theory with a moduli space to start with. Okay, and these models, they resemble in some sense QCD, but they also look very different because you will have KK modes that are much lighter than the actual Reggie trajectories and whatever. So you see, if there was any justification to say that in this QCD working Technicolor models, there is some point with a moduli space that would at least approximately have some spontaneous Brocal conformal symmetry, that would be interesting. But the point is that does not exist, and the explanation you're providing is just not correct.
We should talk more, but I'm not sure that I see what mistake I'm making. I'm just saying that, you know, there is this breaking of scale invariance that's given by the trace of the energy momentum.
Well, this has been a very interesting discussion, but now we're starting to eat into the next time for the next talk. So let's continue this particular discussion at coffee, and now we're going to move to a place where the theoretical data is actually more precise because it's n equals 4. So, no, maybe not?
So anyway. Where are the data?
Thanks again.